let's look at the case of real numbers. So real numbers. This will be our motivation. Suppose we want to solve the equation ax equals b, where ax and b are real numbers. If a is not 0, then we can do a inverse times ax equals a inverse times b. We've multiplied both sides of the equation on the left by a inverse. Now I'm writing a inverse as opposed to 1 over a just for emphasis, and I'll talk a little bit more about that a little bit later. So we multiply both sides by a inverse, and then a inverse times a, that's equal to 1, and so this equation becomes 1 times x equals a inverse times b, which gives us x equals a inverse times b. For matrices, our goal is to find a way to do something similar. We want to solve the equation ax equals b. We already have one way to do that, and that's using a system of linear equations and, say, augmenting and using Gaussian or Gauss-Jordan elimination. What we want to do now, though, is motivated by this real numbers setting. Let's see if we can find a matrix. So we want a matrix, which for the moment I'm going to call A prime, although this will not be our notation that we'll ultimately use. A prime such that A prime times A is the identity matrix. Just as we did over here with real numbers, if x exists, then, so if there's a solution, if this guy has a solution, then we can multiply both sides of this equation on the left to get a prime times a x equals a prime times b, which becomes I times x equals a prime times b. And because I is the identity matrix, this is x equals a prime b. Let's circle that. Now, as any math teacher has probably drilled into your head, whenever you get a solution, you need to go and check to see if it is a solution. Let's check. Is this a solution? So we've already determined that if a solution exists, it must be this guy I circled. But that doesn't mean the solution exists. So let's check to see if it is a solution. Well, is this a solution? Let's plug it in and see. A times a prime b. Okay, well, we want to see, is this equal to b? A times a prime b is equal to a times a prime b. Oh, wait, I know what a prime a equals. It's I, but I don't know what a times a prime equals. So I'm going to actually add in one more condition. If a times a prime is equal to I also, then this guy here is going to be I times b, which is equal to b, and we would win. So this condition I also want. I can't just use this condition here, I also want this condition. And this motivates the definition that we will use for matrix inverse. For the moment, I'm going to just talk about square matrices. We'll talk about non-square matrices in the next lesson. An inverse of an n by n matrix A is an n by n matrix A prime such that A prime times A is I, so that's our first condition over here, and A times A prime is I, and that's our second condition over here. If such an A prime exists, we say that A prime is invertible. Forgot a period over here. Let's look at some examples. If A is 1, 2, 3, 7, then this matrix here, 7 minus 2 minus 3, 1, is an inverse. Show this. Does the 0 matrix, the 2 by 2 0 matrix, have an inverse? In analogy with real numbers, the number 0 doesn't have an inverse. There's no such thing as 1 over 0. So my instinct is to say, no, it doesn't have an inverse. So let's see if I can think of why. OC equals O itself for every matrix C. So we certainly can't have O times C equal to the identity matrix. So therefore, no. The 0 matrix is not invertible. However, whereas the only real number without an inverse is 0, that's not true for matrices. There are a lot of different non-zero matrices without an inverse. For instance, this matrix here, B equals -1, 3, 2, -6, is not invertible. One way to show this is as follows. Suppose it was. Suppose B prime is an inverse of B. And we'll show that we run into a contradiction. Then B times B prime would have to be equal to the identity matrix. In particular, if B, little b here, is the first column of B prime, then B times B prime, using the partitioned matrices we talked about last time, would have to be 1, 0. 1, 0 would be a linear combination again, using what we talked about in the partitioned matrices mini lesson from last time, of the columns of B. But this is false. There's multiple ways to show why this is false. I encourage you to try showing it. And since we've run into a contradiction, we must conclude that our initial assumption that B prime is an inverse of B has to be false. Okay, so B is not invertible. In this lesson, we're going to focus on the properties of invertible matrices and the properties of the matrix inverse operation. And we'll also focus on the special case of 2x2 matrices, specifically how to determine whether a 2x2 matrix has an inverse and how to actually calculate that inverse. In the next lesson, we'll actually learn how to do these things for general matrices.